So in this video, I'm going to recap the different types of controllers that we have to control our systems and the transfer function associated with each. I'm also going to talk about when you would want to use them and why. The other aspect of this video is going to be going through a general solution process for designing a controller of PID and lead-lag form. So let's start with the types of controllers. I've made quite a substantial list. So the first one that we see here is the proportional controller. This is also sometimes called the gain controller. It's probably the most simple form that you can get for your controller. The transfer function is just a constant, k. So the next ones we have are all the different forms of PD, PI, and PID controllers. So we can see that the first one here is a proportional differential controller, and it's abbreviated to PD. This is the form of the transfer function. You can see that you introduce a 0 at negative a, and if you expand out this version of the transfer function, you can make it look like this. In this form you end up with a constant or a proportional part of your controller, and this bit here is also known as the differential part of your controller. This is like the differential gain, I guess. Differential because it gets multiplied by s, and remember that multiplying by s is the same as multiplying by your derivative in time. Alright, so the next one we have is the proportional integrator. This one is abbreviated to PI. You can see that you still have the proportional part, which is the k on the top line, but this time you're also introducing a 0 at negative b and a pole at 0. So this bit here is the integrator, which is where it gets its name from. We also introduce a 0 in this form simply because if you don't, you tend to make your system unstable. So yeah, that's why we have this part in it. If you expand out this transfer function, you can end up with a slightly different form of it. You can see again you end up with your gain or your proportional part of your controller, and you end up with an integrator gain associated with your controller. This bit is called the integrator part because it's divided by s, which is an integrator. So the last one is the proportional differential integrator, PID controller. And what we're doing is we're just putting together the PD and the PI. So you can see that we introduce two zeros, one at negative a and one at negative b, as well as the integrator at 0. So you can see again, if you expand it out, you end up with gains for the proportional part, the differential part, which is multiplied by s, and the integrator part, which is divided by s. So PID controllers require components with a power supply in order to implement them in reality. So for example, an op-amp is a component that requires a power supply in order to make it work. So these are known as active components. So yeah, this is what PIDs are all about. So the alternative to the PID is the lead-lag controller. So again, we can go through the process of adding all the pieces together. So the lead component, we add a 0 at negative z lead. We add a pole at negative pole lead. And the criteria for it to be a lead controller is that the 0 needs to be larger than the pole that you introduce. So lag is the opposite. Again, you're introducing both the 0 and the pole, except that this time the lag part is larger, the pole part is larger than the 0 part. So finally, if you join both of these together, you end up with a lead-lag controller of this form. And the reason that you might use a lead-lag controller is because it can be formed with passive components, so things like resistors, capacitors, and inductors. These don't require an active power supply, so that's why you may be more inclined to use these types of controllers rather than these other ones, which might be a bit more costly. However, I should mention the integrator part here is actually able to eliminate steady state error, whereas the lead-lag controller, or the lag part specifically, is only able to reduce steady state error. It's not able to eliminate it completely. So if we look at what each of the components are doing, we can see that the PD and the lag parts of our controllers, they're there to improve this transient response. So that's reducing the settling time of our system and maybe also changing the overshoot properties as well. The PI and the lag parts of the system are there to improve the steady state error. So as I just mentioned with the PI controller, you can actually eliminate it, but with the lag one, you can only reduce it. And finally, if you have the PID and the lead lag, you get the best of both worlds. You're able to both improve the transient response and the steady state error for your system. Alright, so next I'm going to go through a general process for designing a PID controller. Now this is just, as I say, a general one. It may need modifications depending on your specific requirements, but generally this is how you should be able to do it. So the first step is deciding on your desired pole locations, and you're going to have some criteria that you need to meet, such as a such as a settling time or an overshoot, these types of things. Next, you need to design the PD controller, and the goal of this part is to ensure that your root locus actually passes through your desired closed loop pole locations that you've just decided on. So for that, you need to find where a 0 would need to be placed in order to get your desired closed loop poles on the root locus. And you can apply either this equation, which is like a graphical solution method, or you can use the characteristic equation as well. The next step is then to figure out what gain your desired closed loop poles will now be associated with. Again, if you're using a graphical method, you can apply this equation here, or you can apply this one here if you want to play around with the transfer function equation. Goes on the bottom line here. So once you've done that, the next part is to try and make sure you're meeting the steady state error requirement. So for this, you can add a pole at the origin, which is like the integrator that you were introducing in the I part of this controller. And then you need to place a 0 very close to the origin so that it cancels with the pole at the origin, and subsequently the root locus is not changed very much. If you don't go to the effort of putting in this extra 0 such that you get the pole 0 cancellation, in all likelihood you'll probably make your system unstable, and most certainly you will change the root locus significantly from what you designed back up here, because this part is what was getting you to achieve the settling time and overshoot requirements. So that's the general process for designing your PID controller. So next we have the lead lag design. This has a few extra steps associated with it, but it generally follows the same format. So the first thing you want to do is decide on your desired poles again, using those criteria that you're given, such as settling time and overshoot. This is exactly the same step as the other one. The next thing though is you want to place a lead 0 in a position that minimizes the effect on your dominant closed loop poles. So you have a couple of options. One is to keep the 0 pretty far to the left of your closed loop poles, because remember, the further left or the further away from the imaginary axis something is, the less impact it has on the response. So that's one option. The other option is that you can cancel an existing system pole, and that way you get pole 0 cancellation. And often this is the easiest approach. So either way, you're going to place a lead 0 in some position, and then you're going to need to calculate where a lead pole needs to be, such that you get your desired closed loop poles on the root locus. And again, we have an equation that we can apply in order to do that. You might also be able to use the characteristic equation here as well, depending on how complex your system is. Next, we need to figure out what gain this desired pole corresponds to. And again, if you're using the graphical method, you can use this one on the left, or on the right hand side here we have the equation method that you can use. So when you get to the end of this step here, you will have designed your lead part of your controller, and you will have ensured that you have your root locus passing through the desired poles that you wanted, and you will have picked a gain such that you have your system responding the way that you want it to. So the second part is looking at trying to get your steady state error requirement met. So for this, you need to calculate the steady state error that you have up to this point with the lead controller. Alright, so you need to calculate it with the one that you've designed up to step 4. Once you've got that, you're going to need to look at the ratio of the lag, zero, and pole, and also the ratio of the lead steady state error and the lead lag steady state error. So this is the one you're aiming for. This is what you actually have up to step 4. So the ratio of the the lag, zero, and pole has to be equal to the ratio of these steady state errors. So in order to achieve this ratio, you want to pick the pole such that it's quite close to the origin. So when it's close to the origin, it's going to be quite a small number, and because of this ratio here, it's probably going to end up that your 0 is also going to end up quite close to the origin. And that means that you're going to have effectively pole 0 cancellation between these two values. So that's what step 8 is. It's calculating that lag 0, and you want to double check that you've ended up with your lag 0 and lag pole very close to each other, such that you have this pole 0 cancellation effect, and it means that you've almost unchanged in the rote locus diagram, which is what you want, because otherwise you'd have to go back and refigure out whether you've met your settling time and overshoot or whatever criteria you had back at the beginning. So that's the general process for doing these controller designs. There'll be a couple of examples that you can follow through for some practice. So I'll leave it there. See you in another video.